So when I was sending the title in the abstract, I was a little bit too optimistic. So really, I'm going to talk to you only about merging black holes today, not about all kinds of compact binaries. But let's start with the very basics, although I assume that everybody is familiar about gravitational waves. In 2015, an extraordinary event was detected in gravitational waves, and I say extraordinary because it was much more powerful than we were expecting based on the estimations. And you can see here the waveforms, and I assume that all of you can already tell that this is a gravitational wave signal from two coalescing compact objects. And for some in the room, I assume that you could also tell roughly by just looking at the waveforms what is the mass. Not me, but the people that are actually doing the analysis, right? And one thing that is always blowing my mind is the fact that in this event that we struggle so much to detect, what actually happened during the less than 100 milliseconds right before the merger is that 3 solar masses of energy was released in gravitational waves, and that this is the most powerful, the most energetic event that we have observed, as it is instantaneously 10 times more luminous than all the stars of the universe combined in luminosity. So this is really amazing. And of course, LIGO and Virgo a little bit later, they're not just detecting gravitational waves, but we're able with this data to infer the astrophysical properties of these binary black holes. And the most accurately measured properties of the gravitational wave sources is the chirp mass, which is a combination of the masses of the two components, the effective in spiral spin, which is a mouthful, is the mass average spin of the two black holes projected along the angular momentum axis, and the redshift of the merger or the luminosity distance. These are the three properties that are most well measured. And just from this first detection, we already learned something new in terms of astrophysics. We learned that heavy black holes exist. These were the first black holes that were observed in the range of 25 to 30 solar masses. So until that point, we thought that black holes are more like 7 to 15 solar masses, right? We learned that binary black holes exist in nature. Up to that point, there were codes that were predicting that these systems might exist, but that was the first direct evidence. And on top, we confirmed that there are binary black holes that are close enough that they merge due to gravitational radiation. And since this first detection, there has been another 100 or so more gravitational wave detections. The exact number depends on the false alarm rate that you're choosing to put your cat. And most of them are binary black holes. And so these are the kind of systems that currently are giving us most information in terms of population properties. And we can go into more detail to try to understand the properties of the population. And for myself, the most interesting question, which is how these systems are forming, right? So in the rest of my talk, these are the key points that I will try to discuss and convince you to a certain degree. The first of them is that the black hole spins among the gravitational wave observables, it is the black hole spins that are carrying the most information that can help us distinguish about the formation process of these binary black holes. That one cannot just look at rates or even just distribution of individual properties, but it is the correlation between the observables that actually carry, they have the signatures of the physical processes that are taking place in the formation. That moving forward to really understand the astrophysical origin, looking only in gravitational wave data is not going to be enough unless we wait for the third generation gravitational wave observatories and we have millions of events. But for the time being, the fastest way to move forward is if we try combining data from gravitational waves with other data for other transient events, other populations of compact objects, etc. And that the tools that we're using right now to interpret this data, the formation models, have reached their limit of applicability, and we really need to push forward in improving these models if we really want to interpret this data. So let's go back to the gravitational wave data themselves. And one way to look at them is by looking at individual events, right? And this is what I'm showing here is individual events from GWVTC2. GWVTC3 looks kind of similar. And you have mass ratio as a function of mass, as a function of total mass, and effective spin as a function of chirp mass, I think, is on this axis. And these contours are showing the 90 percentile confidence level for each one of them. And by looking at individual events, we can see already a few very interesting things. We have observed heavy black holes in the range where we believe that black holes cannot exist because the progenitors of these black holes would explode and completely disrupt the star due to a process called peri-instability supernova. There are light mass black holes also in the range where we used to observe black holes in low mass and high mass X-ray binaries. Some of the binary black holes, now we know that they can have mass ratios that are rather extreme, not consistent with one, that they are heavy neutron stars that are not consistent with the kinds of neutron stars that we observe from electromagnetic observations. This is from masses, and if we move to spins, what we can tell from individual events looking at them is that there are several binary black holes which have statistically significant positive chi effective, that there is no individual binary black hole which is inconsistent with a positive or zero chi effective, and there is no individual binary black hole that is inconsistent with what I'm saying here, no individual inconsistent with a zero precessing chi. This is the other component of the spin along the plane of the orbit. But this is looking at individual events. If we look now at all the events together, and you can model the underlying population properties of these events, then you find another level of interesting findings. What you find is that in the mass function of the black holes, there are several features that are emerging. It's not a simple power law. There is a cutoff, there is a nexus at a certain point that carries some information. If you model the underlying distribution of chi effective, you find that there is support for at least a percentage of the population having negative chi effectives or having spins that are misaligned to a degree that are anti-aligned. There is support for several binary black holes having a non-zero precessing component. But a word of caution, all these conclusions are model dependent. So unless we go to a very high number of events, then we should always be careful about the model that is used. For example, here, there is an underlying assumption that the distribution of chi effective is a Gaussian. If you add an additional degree of freedom and you put a cutoff to the Gaussian, then really the negative chi effective cutoff would be very close to zero, a little bit on the negative side. So there are caveats that we should be careful when interpreting this data. And finally, there are already in these 80 or 90 events, there are some indications for correlation and anti-correlation between different properties, between the chirp mass and the chi effective, between the mass ratio and the chi effective. This is from the collaboration paper. There are some more recent papers hinting to an correlation between chi effective and redshift. As we go to higher redshift, we see more spinning black holes, etc. But these are just indications at the time, and we hope that we are going to get something more concrete in the time to come. And all this data that we have and the studies that have been done are what we would like to do is try to use this data to understand the astrophysical origins, I said. The problem is that there are so many formation channels that have been proposed in the literature about how these binary black holes can be formed. In my group, we are working a lot on this first category, the binary black holes that are forming through the evolution of isolated binaries, but the dynamical formation in globular clusters, in nuclear clusters, in open clusters, in disks around supermassive black holes, primordial black holes, triple systems, combinations of all the above. And I here have just a few indicative papers. In reality, if somebody goes to search, probably you need to multiply this number of references by a factor of 10, right? So in the rest of the talk, I will focus on this channel, which is what I'm working on, but some of the points that I will make, I think, are relevant for all the different channels as well. And one thing that I think all the people that are now working on these formation channels would agree at this point is that calculating, estimating the rates of the channels is not a good way to distinguish among the channels, because as already Flor kind of showed the plot yesterday, but there is this nice paper by Ilya and Flor that they are showing that the uncertainties of all these models are so big, especially for binary black holes, that you always find one combination of parameters that give you a rate consistent with LIGO. So we need to go further, and we need to look at the distributions of observables and combined distributions of observables to move forward. And as I said, I believe that the spin is the one that carries most of the information. So let's think a little bit how black holes acquire their spin. To my understanding, to my knowledge, there are 4 possible ways that a black hole can get a spin. Maybe the black hole progenitor has enough angular momentum content that is conserved to a certain degree during the collapse, and the black hole is spinning. There might be an unknown process very late in the evolution of the progenitor star, or during the core collapse itself, some instability that is, I don't know, carrying away a lot of angular momentum in the core and the opposite angular momentum outwards, and somehow magically you come up with a spinning black hole. You can get this black hole spin through accretion or through hierarchical mergers. This last process is the cleanest one. If you have 2 black holes that are not spinning and they merge and they're equal mass, the resulting black hole, we have part of the angular momentum of the binary before. It will be spinning with approximately spin 0.7. So then if that spinning black hole merges with another one in a dynamical scenario, you can have a spinning binary black hole. For this unknown process, the process is the kind of instabilities that people have thought about, gravity waves late in the evolution of a binary, or something like the SAS instability, can indeed carry some angular momentum to the core, but not enough, maybe enough to explain some of the spins of neutron stars, but not enough to produce a black hole that is highly spinning. And I think Matteo would be the person that would know a lot more about this. So the other 2 processes are the ones that can be relevant for the formation of binary black holes through isolated binary evolution. I will talk more about the first one, and this is a whole different discussion. But in short, if you assume that the accretion is limited by Eddington, then you cannot accrete enough material. This is not working. If you allow for accretion super Eddington, this can be a significant component, and we can discuss a lot afterwards about whether this might be happening or not. So what we do know is that stars, young stars, they do rotate. We can measure their velocity observationally, and what we know is that these main sequence stars, after initially they have a pretty uniform composition, but after they evolve a little bit, they form this core and envelope structure. The core is contracting, the envelope is expanding. And there you can make 2 extreme assumptions, right? You can assume that you do not transfer angular momentum within the star at all. So each cell is conserving its angular momentum. And in this case, what will happen is the core will contract, will be very fast spinning, the envelope will expand, will be very slowly spinning, and the core will keep its angular momentum. It will form a fast spinning black hole. If you assume a very efficient angular momentum, then this system will behave like a solid body rotation. As it is expanding, all the angular momentum will go to the outer layers because of the R-square dependence. You will deplete the core from angular momentum, and you are going to form, if you assume that these outer layers now are removed either by stellar winds or binary interactions, since we want a binary black hole, all the angular momentum is removed. You're left with a core that is not rotating. And to the best of our understanding, based on astroseismic observations, but also on observations of young neutron stars, young white dwarfs, we think that we are closer to the latter, to an efficient angular momentum transport within the stellar interiors. And this is a little bit of a complicated plot, but if you assume that initially your star has a specific angular momentum represented by this line here for different initial masses, then at the end of the evolution, if you look at the core of the star and you assume inefficient angular momentum, then this is what you would get, this line here. If you assume efficient angular momentum, then the specific angular momentum of the core will be much lower. And this is the area where we're observing young compact objects. Astroseismic observations point to something similar. So probably what really happens in nature is closer to this. And if you extrapolate, that would give you black holes that are spinning at a negligible rate. So since this is what this is our best understanding so far, let's try to see what are the implications for the formation of binary black holes. There are three different subchannels within the isolated binary evolution. There is the first, the common envelope formation scenario, where you start with two stars, two massive stars at a relatively wide orbit. The primary expands, fills its role, so you have some transfer where you remove the outer layers that are carrying any initial angular momentum. You are left with a helium star that is stripped. This is collapsing to form a black hole, and this firstborn black hole has no spin. Now, the same thing happens in the opposite direction. The secondary star expands to fill its rho slope. Because the mass ratio is extreme, the mass transfer this time is dynamically unstable. You get into this common envelope phase that very efficiently shrinks the orbits, and you are left with the stripped helium core of the secondary star and the firstborn black hole in a very close orbit. And at this point, the orbit is that close. If it is 2 or 1 day and below, then tides can spin up the progenitor of the second-born black hole. And because these helium stars are massive enough that they will not expand in the rest of the revolution, they keep its angular momentum. And so when this star collapses to form a black hole, the second-born black hole can be spinning. Now, in the stable mass transfer channel, the same way you evolve in a similar way, starting from a little bit shorter orbits, but in this time, the reverse mass transfer is dynamically stable. And this dynamical stable mass transfer doesn't shrink the orbit as efficiently. This final configuration has longer orbital periods, so tides cannot spin up fast enough the helium star, and in this case, you expect that the second-born black hole will be negligible spinning as well. And finally, you have the chemically homogeneous evolution scenario where you start with two massive metal poor stars very close together. Tides are spinning up both of the stars and keeping them tidally locked. And because of the high formation, you induce rotational mixing that brings the helium, fresh hydrogen from the outer layers to the core, helium from the core out, and you don't build this chemical gradient to form the core envelope structure that I described you before, but instead you burn all the hydrogen throughout the star and you go directly from a main sequence star to a helium star. Your system remains close in a few days orbit, both of the stars are rotating and both of the stars can form spinning black holes.
There are no winds from helium stars.
There are, and depending on how exactly, what exact assumptions you are making about the angular momentum that these winds are carrying away, you can expand the orbit at different degrees. These are with rather conservative assumptions about these models that are usually calculated with conservative assumptions about the angular momentum that is carried away. So a lot of angular momentum. So you extract, you expand the orbit quite a bit. That's why these black holes are usually rotating, but not extreme spins, but more like 0.3, 0.4. But this is a crucial assumption that we don't know what really happens because the orbit is closed. The winds have not fully accelerated yet from these stars, and they might interact with other compact objects, with other stars, and carry less angular momentum than we think they might. So now that we have this qualitative picture of how binary black holes are formed, in order to actually get predictions that we can compare with gravitational wave data, we need to do what we call binary population synthesis. So there you choose initial conditions from observed distributions that we have constraints observationally. You use your binary evolution model, whatever you have, to evolve these initial stars till double compact object. Some of them will form binary black holes. And then you need to convolve this binary black hole population with a metallicity dependent star formation history of the universe and with a gravitational wave gravitational wave detector selection effects in order to get the predictions for the detectable population or the intrinsic, whatever you want. And there are two ways that one could do this binary evolution. The one is the rapid or approximate or parametric binary evolution. So there one uses some fitting formulae for the properties of the individual stars and approximate prescriptions to model the binary interactions. The advantage of this is that this is very numerically stable, and you can do that in, I say here, 1 CPU second, but it's more like a few milliseconds. So you can do millions and millions of them without problem. The other way that one could do is use our best understanding of how these things work, use detailed stellar structure and binary evolution calculations. The problem there, these are very accurate, the state of the art of understanding. The problem is that these are slow. It takes 100 CPU hours per binary, and very often you need some hand-holding to do just one binary, so not easy. Since I said that I want to, since we said that we believe that spin is the property that carries most of the information, in the models that we try to create, we put special emphasis on the process, on the evolutionary phase that determines the spin. And this is the last phase where you have a helium star, stripped helium star, and a compact object. So we did this part of the evolution using detailed simulations. We used the open source publicly available MESA code. And the rest of the evolution, we followed it through a rapid parametric simulation using the cosmic code. So we tried to do the best we could given the constraints that we had. And when you do that, you can get combined distributions of observable properties like the one that I'm showing here, Zerp mass versus chi effective. And these are the 90 and 99 percentiles, the two contours. And what we found is that chemically homogeneous black holes formed from the chemically homogeneous channel populate this part of the parameter space of high masses and high spins. And because they are high masses, they're easily detectable by the detector and they're being picked up even though they're pretty rare. And then common envelope evolution is populating this part of the parameter space of lower masses and higher spins for some of them. Some other have low spins if they happen to be a little bit further away, while stable mass transfer is populating mostly this part of a little bit higher masses and no spins because the stable mass transfer is resulting to wider orbits. One can overplot some gravitational wave data from GWTC2 in this specific case. And what you can see is that this model cannot reproduce the entirety of the data. So there are at least 20% of the observed events that are not consistent with the specific model that we're showing here. But you can reverse the picture and say that many of the events are reproducible by this model. So we can make the working assumption that the model that we're showing here is producing a large fraction of this of the observed population. Then one can go and ask the question, okay, this is what is the detectable population, but what is the underlying population? What is the true intrinsic population of binary black holes? Not only the ones that LIGO and Virgo are seeing. And if you make this question, if you remove the selection effects, what you find is that there is a very large population of highly spinning black holes, a significant population of highly spinning black holes that LIGO and Virgo is not detecting because of the selection effects, because Virgo and LIGO are very sensitive to high masses, and so this part of the population is being missed. And we were looking at this figure here, and we thought, wait a second. This spin is coming from the second-born black hole in the model that we described. And this is chi effective of 0.5, which means that the second-born black hole has an almost extreme spin in these cases. So these systems, the progenitor of this second-born black hole must have been spinning very fast. And so what happens to a very fast spinning star that is collapsing? It's producing a long gamma ray burst, right? Based on the collapsar model. So since in our models, we did have the information about the structure of each of the star that was producing these second-born black holes right before the collapse, we could do the following exercise. We could go cell by cell. We knew the density profile, we knew the rotational profile, and we could go cell by cell and see from each cell which part of the cell has enough angular momentum so that when it collapses, the angular momentum, the specific angular momentum of this part of the cell is higher than the specific angular momentum of the ISCO. And in this case, this part of the cell of the star would not fall directly on the black hole, but it would form first a disk. And doing so, and this disk then would be accreted on a viscous time scale. So doing so, we could calculate for which one of these collapsing stars you would expect to form a disk, which would then give you a long gamma ray burst. And we can go in the previous picture that I showed you and overplot with these blue contours, when do you expect to get a long gamma ray burst? And it is exactly from this part of the parameter space that LIGO and Virgo are not sensitive to probe. But still, one could go to each one of the events that have been observed so far and calculate the probability that for this specific event, when the binary black hole was formed, not when the merger happened, when the binary black hole was formed, which can be hundreds of million years or giga years earlier, a long gamma ray burst accompanied the formation of this binary. And you can find that at least for these two of these systems, the probability is more than 50%, 80% for one of them, while there are another dozen of systems with non-negligible probability. And one could go a step even further and say, okay, I can plot the merger rate density as a function of redshift, just focus on the black line here, that is the total merger rate density. The colored lines are for the different channels. And you can plot also just the rate density of, make some assumptions about the beaming fraction of this long gamma ray bursts and the energy efficiency with which you are converting the mass into the disk mass into gamma rays, and you can estimate based on these uncertain assumptions a rate for long gamma ray bursts. And then you can go and you can overplot some observed derivation of this, and you can find whether you agree or not. Now I choose some parameters so that it agrees, but the real question here is, do my model produce more long gamma ray bursts than they are observed for reasonable values? And so that is actually a robust constraint that one can put to any formation channel, that you need to be careful that whatever you're saying here should not overproduce long gamma ray bursts. And in our model, using extreme or favorable values, we can match the rate, but for most cases, we get a lower rate. So we're good to go. We are not violating constraints from long gamma ray bursts that already put some constraints, right? Now, I said that in the models that I showed so far, this part of the evolution, all these different binary interactions, are followed with these parametric codes that are very approximate. What is really the problem with these codes, right? This is a picture that I stole from Floor, and I think it depicts very well the status of our field. We are building all these complicated models of binary interactions, population synthesis, convolved with cosmological simulations. But at the heart, everything is based on a number of stellar evolution tracks that were run back in the late 90s, and some fitting formulas that were derived on these few tracks that have some very severe assumptions. These fitting formulae, they're assuming that the stars are single, they're at constant mass, so no stellar wind in the initial fitting formulae, they're not rotating, and they're always at thermal equilibrium. So no matter what happens when you have a binary interaction, your star is at thermal equilibrium. And you put stellar winds and binary interaction mass loss on top of it by just saying that you are starting from a 16 solar mass. If you remove a little bit of mass, you're going to move to another track that looked exactly like the other ones, and just do some calculation for rejuvenation to say that, okay, now I'm going from here to here, but on a track that looks like a constant mass track, right? And this only works if the mass loss is very slow, and mass loss either because of wind or because of binary interactions. But this is causing a number of problems. One of them, the radius estimates, when you add mass loss or mass gain on top of it, are very off. You cannot calculate the mass transfer stability of these systems very well. You can only estimate it, and these estimates can be very off. You cannot calculate correctly the mass transfer rate. You cannot get information about the structure of the collapsing stars. You cannot take into account angular momentum transport processes between and within the stellar components. You cannot take into account mixing processes, etc., etc. So can we do better than this? I think that now we start to be able to do that. And this is what we're trying to do in the Poseidon collaboration, where we're trying to build a new population synthesis code that is based solely on detailed stellar structural binary evolution calculations. So we're running huge grids of not tens, but hundreds of thousands of binaries at all kinds of different evolutionary phases. And we're using these self-consistent calculations to follow the evolution of a binary from XAMPS until the formation of the compact object. And now I want to share you some recent results that are still unpublished, but I'm very excited about them, which is the first simulation that we have for the formation of binary black holes. But before we get there, let me explain to you what is really the problem here, right? I said that in rapid population synthesis codes, mass loss does not impact the stellar structure. I'm giving you here an example from the SIBA code, but it doesn't matter that the heart is SC in all these parametric codes. So it's the same thing, single stars here. And you see different masses going from 10 all the way up to 100. And you see that all the stars they're evolving to become red supergiants of a few thousand solar radii, no matter how much wind is applied to it. And what happens to these stars? They're getting to this regime of either LBV or dust-driven winds that are removing the whole envelope of up to 60% of the mass is removed due to LBV winds or dust-driven winds. And you end up with black holes that are about 20% of the initial mass of the stars. But we do know, not now, but from the 80s, that when you apply winds to a massive star, the stellar structure is reacting, and the star is not expanding, but it is turning back towards the blue before expanding to a radii of 1,000 before becoming red supergiants. So we do know that this effect is important for very massive stars, but in the binary black hole modeling community, we have neglected this effect. But can we actually do it? I think the answer is no here. Now, these are a little bit more updated tracks compared to what I showed you before by Mede and Menet. And what we find is that when you go to stars above 60 solar masses, these stars never become supergiants. They don't go to the Hayashi track. They turn back towards the blue, and they don't lose a lot of mass in dust-driven or LBV winds. Instead, they lose only about 20% of their mass. They lose most of their mass as either Wolf-Rayet or line-driven, and they form black holes that are 40% of their initial mass because of this reduced wind. And some of the stars, the most massive ones, don't even expand at all after their main sequence, because during the late stages of the main sequence, you have removed enough mass that you exposed helium-rich material, and you turn from end of the main sequence to Wolf-Rayet stars directly. All this is not new, but it is not taken into account in the formation of binary black holes. So what happens? We said the stars are not expanding. So one new thing that appears when we're talking about solar metallicity always is that if you happen your primary star to be in the regime above 90 solar masses or 80 solar masses, and the secondary to be a little bit lower, below 50, that the stars are expanding a lot, then you can avoid the first mass transfer altogether. And only after the formation of the first-born black hole, the secondary, which is less massive and expands, can interact and form a black hole either through stable mass transfer or common envelope. So new formation channels are emerging. Another thing that happens is that you can form very massive black holes. So with blue dots here, what I'm showing is the initial final relation between ZAMS mass and black hole masses. So you see that for stars of about 70, 80 solar masses, you can form black holes at solar metallicity of 30 solar masses, right? But these are single stars. If you take into account binary interactions that might happen throughout the evolution, then the spread is quite big, and you can populate, depending on when the interaction happens in the evolution of the star, you can populate everything in between here. To this, you need to add things like changes in the stability of mass transfer that was not calculated correctly in rapid codes. Usually in rapid codes, you use some approximations about what we call critical mass ratios that are different in whether the star is convective or whether the star is radiative, and some fixed values are used. But if you do the calculation numerically, so each one of the square is different run for intermediate mass stars, but you can transfer it. We have it in Poseidon for all kinds of masses. What you can see is that when you have radiative envelopes, is everything below this line here. So you can, let's look at the green curve. Everything which is green is stable mass transfer. Everything that's gray is unstable. You can see that for a radiative envelopes, the Q-crit is not constant, but it varies significantly by a factor of 2, depending on when the mass transfer is happening. And when we are going to deeply convective envelopes for late case B and case C mass transfer, the critical mass ratio is more like 2 rather than 0.78 that was used in most parametric codes. So stability of mass transfer is different. Our assumption that the first born black hole has 0 spin that I made earlier at the beginning of my code is also an approximation, because what happens here is that for some of the systems, the binary can remain. So these are different runs again, different orbital period initial, different mass, specific Q. I'm showing here a slice. For some of these binaries, they can remain close enough during the first mass transfer that tides can give a little bit of spin to the first born black hole projector and give you spins of 0.1 or 0.2 instead of the 0 that we assumed in the first models. So if you put all together these ingredients that I told you, and again, I should stress that what I'm showing here should not be compared yet with gravitational wave data, because these results are only for solar metallicity. But we can get some very valuable, nevertheless, we can get some very valuable conclusions. One of them is that you can form binary black holes at solar metallicity at non-negligible rates. This is something that all current rapid population synthesis codes agree that you cannot form merging binary black holes at solar metallicity. Another thing is that you have new formation channels that are emerging. I explained to you earlier. You can have most of black holes, as our intuition says, are formed in the range of 8 to 15 solar masses, but there is a long tail of black holes, even emerging black hole binaries, that can be as massive as 30 or a little bit above solar masses. So a 30 solar mass black hole does not immediately mean that must be coming from a low metallicity environment. And the first born black holes, the blue histogram here, is not really spinning with a 0 spin, but it has more like a width in its distribution of 0.1 to 0.2, even at very efficient angular momentum transport. So I'll put up again my key points, which are the same as I showed you earlier, and I will take any questions that you might have.
Are there any questions, even on Zoom? This is great. So, yeah, the spins are very informative. Do you extract other observables besides chi effective? Like if we were able to measure individual spins and their orientations, let's say, that would you be able to see resonances appear? I mean, we'll have discussed this.
So here actually, I'm plotting individual spins, but I don't have the orientation here in this figure, but this is certainly an observable. You expect that for these black holes, binary black holes, you don't expect to often see negative chi effective. You might get it, but at a very small rate. You would not explain the support that you've seen in data. But you can certainly have some distribution of cos theta, let's say, or some distribution of chi p. We're producing these plots as we speak. We just needed to rerun something because something was wrong and we didn't extract the data from the simulation correctly. But you do expect to have a range of chi p's. I don't know if it agrees with the inferred one. I would guess that no.
I mean, those measurements are still pretty bad, but they will get better hopefully. So
yes. So it is what determines how much misalignment you will get in all these formation channels is the supernova kicks in black holes, which are quite uncertain. So variations of this assumption can grow a little bit the spread of chi-p or make it smaller, but I don't think still that you can get this distribution that picks at 0.2 that is being proposed in the LIGO Virgo paper.
There is a question online from Matteo.
Yeah. Hey, Tassos. Great
Hey,
talk.
Matteo.
Hi. Good to see you. And so you stressed out the problem with rabbit codes that do not account for the stellar structure reaction to massless and ways to maybe like implement that. You didn't comment much on the fact that, especially for the more massive stars, even detailed models struggle because we really don't have a physically sound prescription for mass loss in, for example, the LBV phase, and even red supergiants at high luminosity. We don't even know if those winds are Middle-East dependent. So I was wondering how much that effect might change your results, and have you explored playing a little bit with different prescriptions, even if, as I said, they don't really exist?
Right. So for solar metallicity, it turns out that in this model here that I showed, we included LBV winds in the same way that is usually included in the rapid binding population synthesis codes. You put an area of the parameter space, and when you enter that in the HR diagram, you put a very high mass loss. But what we found is that the effect is very small. So we tried a few things. We tried with and without LBV winds. The difference is quantitative, yes. Let me see if I have it at the end. I don't. I do. So this is the difference between having and not having LBV winds. I don't have the mass function. The mass function looks similar, a little bit shifted. Another thing that we tried is to change Wolf-Rayet winds. But again, the change was quantitative but not qualitative. What really happens is that these stars do not lose, the black hole progenitors do not go to the dust-driven cool wind regime. They stay very little. Even when you go there, for example, you can see this 60 solar mass track, you go a little bit, but as soon as you increase a little bit the mass loss, the star turns back. So at solar metallicity, I don't think that this is very crucial because you are losing a lot of mass earlier on. When you go to lower metallicity, the stars will expand more. They will enter for a longer period in the LBV and dust-driven wind regime. And there, what you are mentioning is certainly going to be more important.
Right. Thank you.
Brian also has a question online.
Hi, Tassos. Thank you for the talk. I'm not familiar with the literature on this, but I guess one question I had is, what are your thoughts on the reason that high mass X-ray binary black holes are spinning rapidly, right? Because they would be the first black hole in their binary. So I guess I'm wondering how that...
Scientifically speaking, this is what keeps me awake in the night. And my views have changed over time. We have tried, I think Matteo has participated in some of these conversations. We have tried to think if there are ways that you can start, in some cases, from a closed binary from a closed binary that the progenitor of the first-born black hole would be always tidally locked, never expand because it goes through a late case A mass transfer and not case B, and it would keep enough spin. And what we have found repeatedly, unfortunately, is that if we assume efficient angular momentum transport, the spin will at best be small, so not as the observed one. If you assume inefficient mass transfer, then you get conflicting results with the gravitational waves. So that leaves two things that might happen. Either that these measurements are not correct, which I hope that that's not the case, because that would remove some very interesting and challenging observational constraint, or that the mass, that the spin is coming from accretion. Now, there needs to be a lot of fine tuning for that to happen. But at the same time, recently, it has been stressed, something that should have been obvious beforehand, that all these high mass X-ray binaries, they look alike to each other. They are almost filling the Ross lobe, massive star almost filling the Ross lobe, but not quite filling it. And the argument that was stressed was that for black holes, in order to be bright X-ray binaries, you need to have a disk formation. And this happens only for specific conditions when the donor star is filling more than 80% of the star. So what that says is that there is a very strong selection effect of the systems that we can observe as wind-fed high-mass X-ray binaries. And that allows us to think of fine-tuned parts of the parameter space that give you the one and the other. I have some thoughts of how this might happen. I think we shouldn't constrain ourselves with accretion limited by the Eddington limit, because radiation GRMSD simulations have shown that this is not the case. But I don't have a self-consistent picture yet of how this might happen. I have some ideas of which are the cases, but nothing that I can convince somebody before doing detailed calculations. So it's a challenging topic that we need to understand.
Thank you.
So a very long way of telling you I don't know.
Thanks for the talk. I wonder if you could give us, I mean astroseismologists, in this case, a summary of all your models that go into your Poseidon framework of the convective cores along the evolution, because we have measurements now of that for stars born with convective cores. So that could help us look out for more massive stars that would help you to better constrain the models. You see what I mean? Right, so from the SAMs to the explosion, I would like to get a table or a plot of whatever convective core mass you have along the evolution.
Yeah, so this is doable, but
yeah.
I don't think that the part of the parameter space would be that much different than looking at single stars.
Right, but I want to calibrate single stars. That's what I want to do.
So
that go into your synthesis.
Yeah.
Right?
So what I'm saying is that looking at the binary grids that we have run, it can be done. The ranges will be a little bit different, but not qualitatively. So looking at single stars simplifies the problem. But yeah, so this is easy to be done. We have a lot of models with different assumptions for single stars, but we're not the only ones, right? So.
But you have them, and so I'm curious to know what your constraints are, because we have a factor 2 difference in core mass by now.
So that would calibrate things like overshooting as well. Yeah. And for which masses? Which is the most massive stars for which?
For the most, we're building up. We're at 9, and we're going up to 20.
Okay.
I need some more time.
Yes.
So I was looking at your plot where you compared the predicted from 3 binary evolution channels masses and high effectives versus.
I think it's here. Okay. Yes. So.
Am I understanding correctly from those plots that you favor, for say GW15 or 914, you favor chemically homogeneous evolutionist as a scenario to produce that?
If you take at face value the specific figure, then yes. But so one problem with the specific models for chemical homogeneous evolution that bothers me, I'm going to the nitty-gritty details, is that what you find is that most of these binaries, in order to get a non-negligible rate, these are detailed models that are coming from Pablo Marsand and Debuchon. They were kind enough to let us integrate them in these models here, is that most of them, they get into contact and they are in contact binaries even at ZAMs. Now, this bothers me a little bit because that means that they were in contact in the pre-main sequence phase and in the accretion phase. And I don't see how that could happen and be self-consistent. So if you remove all the ones that are in contact at ZAMs, then you are left with a very slim sliver of the parameter space. But that again is very dependent on exactly the question that you asked earlier, which is, these helium stars, don't they have winds? What do you do with them? And there is a critical assumption there about the angular momentum that you are carrying away with the wind. And if you make more favorable assumption, then you grow this part of the parameter space, you can have enough chemically homogeneous stars without having to dig into the ZAMs. That's why I'm saying, do I trust quantitatively the prediction? No. But if chemically homogeneous systems exist in roughly the rate that we see there, I don't know what's happening, then they would be in this part of the parameter space.
Based on what we know, what is your opinion about evolution in 09?
What do you mean? Where it is coming from?
Where is it coming from? What is the channel for which this binary was made?
I cannot tell you, because all this, if you look individually at each one of the channels, even if I believe at face value exactly this model combination, you have some tails, right? These things are overlapping. They're not as clean as you see them here. Even if you remove this chemically homogeneous, this part of the parameter space will be still populated. So I don't know, and then you are varying things, and you can create a little bit of different. I cannot give you an honest, real answer that I believe myself.
No, it's 4:30, but I've been told that there are some delays in setting up the reception. So there was a raised hand. So go ahead.
So thanks a lot. So this is very interesting. I'm a little out of the field, so like this is a very basic question. But as far as I understood, all your arguments you put here are thinking about like isolated binaries. But in fact, the detections of gravitational waves we have would be from different channels. So for instance, one I'm maybe more familiar with is the dynamical channel. And I assume that this would also populate a part of your parameter space.
Yes.
I assume maybe at left and high masses. So I was wondering how this compares with your what you were describing.
The reason I said that some of the things that I will talk about are touching the other channels is exactly the spins. So what I described about the spins holds for the dynamical formation as well, only that there you are forming your black holes by themselves, right? Individually. So you would expect all these black holes to have initially very small spin, because there is no way to spin them up through tides or one of the models that we have shown here. So what would that mean? That you would only get this part of the parameter space. And then on top of that, what you would get is some second generation mergers that would populate higher masses and higher spins, but in a symmetric way around zero. So you would get some systems here and some systems here.
So I'm trying
And
to
this
understand
system.
this argument. Why do you say that in dynamical channel, the black holes are formed in isolation? Don't we know from, Selma Deming's work and others that most massive stars are in binaries?
But not in globular clusters, these soft binaries are being disrupted early on. So
okay, so they
So
you form black holes, there are no
So you don't form, and the mass is forming binary black holes through binary evolution is a very inefficient method. So the mass that you have in globular clusters is so little that you would not form black holes through.
But I mean, in terms of the spin, right?
Yeah, but you still need to form black holes in binaries from a binary.
My point is that most massive binaries they don't make binary black holes, but most massive stars are in binaries.
Yes.
And the black holes.
But how do you form in globular clusters? The way you form the binary black holes is the following: you have stars all over, initially through a mass distribution, and then the most massive stars evolve when they start exploding, and they are forming, some of them, black holes. Then you start forming neutron stars, and you start exploding all the massive stars. Let's say at some point after 10 gigayears, you are left only with 1 solar mass stars or less, neutron stars, the ones that have not been ejected, and black holes. And because of dynamical friction, these black holes initially are very far from each other. They cannot meet each other. Because of dynamical friction, they sink to the center, and only then they start interacting to form black holes.
I completely agree with you. I'm just wondering why black holes cannot have high speed in the initial high speed.
Because it is very rare to given the little mass that you have in globular clusters, to form from a primordial binary a helium star and a black hole next to each other that you spin them up. This is a very rare process. You cannot do it in globular clusters. And the progenitors of these systems are also very wide binaries that you would disrupt in globular clusters to start with. So you don't see this symmetric distribution, certainly. You might have some contribution, but certainly you don't, the dynamical formation is not the dominant channel.